In this video, we're going to conduct the goodness of fit test. To test hypotheses regarding a distribution, use the steps that follow. Step 1. Determine the null and alternative hypotheses. So our null hypothesis is going to be that the random variable follows a certain distribution. What that certain distribution is depends on the specifics of our scenario. The null hypothesis will be that the random variable does not follow the distribution stated in the null hypothesis. So our null hypothesis is going to be that our variable follows the distribution. Our alternative hypothesis will always be that it does not follow the distribution stated here. Step 2, decide on a level of significance alpha depending on the seriousness of making a type 1 error. Step 3, Part A, calculate the expected counts E sub I for each of the K categories. And we're going to do that by E sub I equals N times P sub I for I equals 1, 2, and so on up to K, where N is the number of trials, P sub I is the probability of the ith category, assuming that the null hypothesis is true. So we're going to calculate all of the expected values for each category that we're dealing with in our scenario. Part B, we have to verify that the requirements for the goodness of fit test are satisfied. So this is what we discussed in the previous video. All of the expected counts have to be greater than or equal to 1. So again, that's really a requirement about the sample size or the number of trials. We have to repeat the experiment or have a large enough sample size so that all of the expected counts are greater than or equal to 1. And no more than 20% of the expected counts can be less than 5. So we would like all of the expected counts to be larger than 5, but we can settle for some of them being less than 5 as long as it's no more than 20%. So there we're checking for the conditions to be able to use the chi-square distribution. Step 3, Part C. Now here we're going to split it depending on if we're going to use the classical approach or the p-value approach. So if we're going to use the classical approach or the p-value approach, either way, we're going to calculate the test statistic. And we're going to call that chi-square naught. Chi-square naught. Now chi-square naught is equal to the sum of O sub I minus E sub I squared divided by E sub I. So again, we're going to do that whether we're using the classical approach or the p-value approach. So again, what does this mean? For each category, we're going to take the observed counts or the observed frequency and subtract the expected counts or the expected frequency, square that result, and divide by the expected count or the expected frequency of that particular category. Note that O sub I is the observed count for the ith category. So again, observed minus expected squared divided by the expected. So we're going to do that for each category and add that up. That gives us chi-square naught. Again, whether we're using the classical or the p-value approach, that's what we do next. Now, step 4. We're going to determine the critical value using either Table 8 or technology. And it's also going to depend on our level of significance. So we're going to find chi-square sub alpha. Now, one thing that's different about a chi-square test is that a chi-square test is always a right-tailed test. So alpha will always be the area in the right tail. So we're going to have the area in the right tail. We're going to figure out what that critical value is. And again, the chi-square distribution will have k minus 1 degrees of freedom, again, where k is the number of categories, not the sample size. So we're going to then compare our test statistic to this critical value. And if our test statistic falls to the right of the critical value, then we'll reject the null hypothesis. Otherwise, we will fail to reject the null hypothesis. Again, this will always be a right-tailed test. Now again, our directions here say compare the critical value to the test statistic. I personally prefer to think of that the other way around. Compare the test statistic to the critical value. Again, if chi-square naught, our test statistic, is bigger than chi-square sub alpha, the critical value, then we're going to reject the null hypothesis. If it's less than or equal to, then we will not. And we'll state our conclusion. Now, if we're going to use the p-value approach, then the p-value will be the area to the right of our test statistic. So again, this is always a right-tailed test, so the p-value will be the area to the right of that test statistic. So we can either approximate that p-value using table 8 from the appendix of our book, or we could use chi-square CDF in our calculator to find the p-value, or we could use the chi-square calculator in StatCrunch to find our p-value. Now we also have a technology option for step 3. And so if we have technology option, then we can use a statistical spreadsheet or calculator with statistical capabilities to find the p-value. And so we'll discuss that a little bit later on. If the p-value is less than alpha, we reject the null hypothesis. If the p-value is greater than or equal to alpha, we do not reject the null hypothesis. That's step 4. And then step 5 will state our conclusion. So again, this hypothesis test works like all of the other hypothesis tests that we've done. The difference again in this one is that we're using a different distribution to model the scenarios. So we're using a chi-square distribution instead of the normal distribution or the t-distribution. But otherwise, the test works pretty much the same. It is always a right-tailed test, though, when we're doing a goodness of fit test. So let's take a look at an example. So peanut M&Ms. According to the manufacturer of M&Ms, 12% of peanut M&Ms in a bag should be brown. 15% should be yellow, 12% red, 23% blue, 23% orange, and 15% green. A student randomly selected a bag of peanut M&Ms. He counted the number of M&Ms that were each color and obtained the results shown in the table. Test whether peanut M&Ms follow the distribution stated by M&M Mars at the alpha equals 0.05 level of significance. So again, what's going on here? Well, according to the manufacturer of M&Ms, which is M&M Mars, they're saying that peanut M&Ms should be 12% brown, 15% yellow, 12% red, 23% blue, 23% orange, and 15% green. This student got 53 brown, 66 yellow, 38 red, and so on. And so we're supposed to determine, is this distribution of colors stated by M&M Mars accurate or not? So what we have right here in this column of data is the O sub i's. This is the O sub i's. These are the observed results from the student's data. So like this is category 1, category 2, category 3, 4, 5, and 6. So we have 6 categories here. What we have to figure out is the E sub I. So we have to figure out how many of each color should be expected. And is what we observed different enough from what is expected to say that the expected is incorrect? Well, how do I go about figuring this out? Well, the first thing I need to know is how many M&Ms do we have altogether? So if we add up 53 plus 66 plus 38 plus 96 plus 88 plus 59, that is 400. So N equals 400. We had 400 observations of colors of M&Ms. And so I'm going to calculate E sub I based on that. Now again, brown, according to our problem statement, we're supposed to have 12% brown. So if I take 400 times 0.12, that is equal to 48. I would have expected 48 of the 400 M&Ms to be brown based on the fact that it's supposed to be 12% brown. If I take 15% of 400, that is 60. So again, 15%, because 15% of M&Ms are supposed to be yellow, that is 60. So I would have expected 60 of the M&Ms to be yellow. Now red is 12%, so that will be 48 again. 12% of 400 is 48. Blue is supposed to be 23%. Well, 23% of 400 is 92. I would have expected 92 of the M&Ms to be blue. Orange is also 23%, so I would have expected 92 of the M&Ms to be orange, and green is 15%, so that would be 60 again, like yellow. So again, these are the expected values, these are the observed values, and we want to test to see whether M&Ms is following the distribution stated by M&M Mars. Well, so I need to state my null hypothesis more clearly, and I need to state my alternative hypothesis more clearly. So my null hypothesis is going to be that peanut M&Ms follow the color distribution stated by the company, by M&M/Mars. So in other words, my null hypothesis is that the population of peanut M&Ms really is 12% brown, 15% yellow, 12% red, 23% blue, 23% orange, and 15% green. I'm just being a little lazy. Instead of writing all those percentages, I'm saying, yeah, it's supposed to be this. And the alternative hypothesis is going to be that that color distribution is wrong. So my alternative hypothesis will be that peanut M&Ms do not follow the distribution stated. So my null hypothesis is that the color of peanut M&Ms do follow the distribution stated by M&M Mars, and my alternative hypothesis is that the color of peanut M&Ms do not follow the distribution stated by M&M Mars. Now, our problem told us we're supposed to use a 0.05 level of significance, and so we can do that provided that we meet the conditions to conduct the test. So we had two conditions. All of our expected values have to be greater than or equal to 1, and in this case we do meet that condition. All of our expected values are greater than 1, and no more than 20% can be less than 5. Well, all of our expected values are greater than 5, so we meet those two conditions. So we are able to use the chi-square distribution to model this and conduct our test. If we do not meet the conditions, there's a couple of options. One option is we could combine categories, if that's possible, in order to meet the conditions, or the other possibility is we would have to use non-parametric methods. Now, so we know that we can conduct the test. Next, I either have to use the classical approach or the p-value approach to conduct this test. Either way, we're going to have to calculate chi-square naught. So if we calculate chi-square naught, I'll write down our formula again. That's going to be the sum of the observed minus the expected squared divided by the expected. I really should have my summation symbol a little bigger. We're doing the sum of all of that. So I just want to be clear that sum is not just for the numerator. That sum is that whole thing. So for each one of these, I'm going to have to do this calculation. So I'm going to take 53, the observed for brown, minus 48, the expected for brown, square that and divide by 48, the expected for brown, plus 66, the observed for yellow, minus 60, the expected for yellow, squared, divided by 60, the expected for yellow, plus 38, the observed for red, minus 48, the expected for red, squared, divided by 48, the expected for red, plus 96, the observed for blue, minus 92, the expected for blue, squared, divided by 92, the expected for blue, plus 88, the observed for orange, minus 92, the expected for orange, squared, divided by 92 expected for orange. And last but not least, plus 59, the observed for green, minus 60, the expected for green, squared, divided by 60, the expected for green. So now I just have to type this in my calculator to see what that value is. So if I bring in my calculator, parenthesis, 53 minus 48, close parenthesis, squared, divided by 48, plus, parenthesis, 66 minus 60, close parenthesis, squared, divided by 60, plus, parenthesis, 38 minus 48, close parenthesis, squared, divided by 48, plus, parenthesis, 96 minus 92, close parenthesis, squared, divided by 92, plus, parenthesis, 88 minus 92, close parenthesis, squared, divided by 92, plus, parenthesis, 59 minus 60, close parenthesis, squared, divided by 60. So again, in each case, it was observed minus expected squared divided by expected. We add all of that up, and so I get a chi-square value of 3.569 if I round to 3 places. So this is approximately 3.569. So if I'm going to use the classical approach, I need to find the critical value to compare this to. Now in this particular case, we have 6 categories. So K equals 6, which means our degrees of freedom will be 5, 6 minus 1. So I'm going to be looking at a chi-square distribution with 5 degrees of freedom. So the degrees of freedom equals 5. This area in the right tail, because we're always doing a right tail test, is going to be alpha equals 0.05 because that's our level of significance. This is a chi-square test, and there's 0. I need to figure out what is that critical value. So again, my choices are to either use the chi-square table to figure that critical value or to use the t-calculator in StatCrunch. I cannot use my calculator to figure that out. I don't have an inverse chi-square command on my calculator in order to be able to figure that out. So it's got to either be the table or chi-square calculator in StatCrunch. I'm going to use the table. So if I bring in my chi-square table, alpha is 0.05, so that's the area in the right tail. I have 5 degrees of freedom, so I'm going to use that row. And so my critical value is 11.070. So this critical value is 11.070. That's my chi-square sub alpha. So by the classical approach, I'm going to compare 3.569 to that. Well, 3.569 would be over here to the left of the 11.070. So that tells me do not reject. So I'm not going to reject the null hypothesis. Now, if I want to use the p-value approach, then I have this chi-square distribution, and I have 5 degrees of freedom, and so I can use my chi-square CDF command to figure out what that value is going to be. So my command will be chi-square CDF. In this particular case, my test statistic is 3.569. Since it's always a right-tailed test, my p-value will be the area to the right of that 3.569. So this will be the p-value. So again, I can use chi-square CDF to find that area. So chi-square CDF, 3.569 to a big number, 10 to the 99, and I have 5 degrees of freedom. So I can use chi-square CDF. I could also use the chi-square calculator in StatCrunch as I showed you previously. So if I bring in my calculator, distribution. Option number 8, chi-square CDF. We have 3.569 as our left bound. The right bound's a big positive number, so 10 to the 99. We have 5 degrees of freedom. Paste. And so that gives me 0.6130 if I round to 4 places. So this is 0.6130. That's our p-value. So our p-value is bigger than alpha, so that's bigger than 0.05. So again, that tells me do not reject the null hypothesis. So whether I use the classical approach or the p-value approach, as usual, I get the exact same conclusion. That should always happen. You're going to get the same conclusion either way. So we do not reject the null hypothesis. So in other words, as far as we can tell, the null hypothesis is true. Peanut M&Ms do follow this distribution of colors stated by the manufacturer.